So let's crack into this. The 4a asks you to define what is meant by a normal subgroup of a group. Well, 2 marks, just give the
small definition.
Small definition. So let H be a subgroup G. H is normal in G if for all little g in G, this is it, GH equal to HG, i.e. the left cosets and right cosets are always the same. Hi, George. Hi. Left cosets and right cosets represented by an element of G are always the same. Probably no harm to give, just say the definition of this notation. It's the set of all GH such that H is in H. Yeah. And HG similarly. I think that was the definition given. You could phrase it alternatively as well. So alternatively or equivalently, you could phrase the central property as saying for every G in G and for every H in H, G inverse is always an element of H. Another way of saying it. Emphasizes the action of by conjugation. But I think that was the original definition we get. Okay. Question B then introduces the dihedral group, and it gives you a summary of what the dihedral group is here. It's a group of symmetries of a regular polygon with n sides, triangle, square, pentagon, etc. And it's generated by 2 elements, a rotation, basic rotations, and a reflection, S. These are subject to the relations, so R to the n is E, the identity element. S squared is the identity. And S and R commute according to this relationship here, that SR is R inverse S. And then it gives you this kind of standard form. So the 2n elements of dn can be expressed in standard form. You can always express a symmetry of the polygon as some amount of rotations after, well, either some amount of rotations or some amount of rotations after a reflection. Right, so R to the I, S to the J. The options for J are either 0 and 1. So S to the 0 would be by definition the identity, so that in effect it isn't there. Or S to the 1, so it's just S. So S is either there or it's not. And then you've some power of the R. Everyone okay? Just on just kind of take that information in. So that gives you the kind of context in which to think of the dihedral group. So we looked at the various parts. Prove that E and R cubed is a normal subgroup of D6. Okay. So H is equal to E cubed. Okay, so it comes up. I mean, I'm just making this note for my own benefit. So this will be rotation by 3/6 of a full turn. So basically, this is rotation by pi radians. Don't say whether it's clockwise or anti-clockwise. It's the same for rotated by pi radians. Okay, so how do you prove this normal? Well, we'll just use the definition we've just quoted for normality. So we have to prove that our left coset is equal to the right coset generated by the same element, and we have to show that for every element in G. Okay. And the question just gave us a standard form to think of for elements, r to the I, s to the j. So I would make use of that. Okay. So a typical element of G is r to the I, s to the j equals 0 or 1, I between 0 and 5. Sorry, are we in D6 yet? Yeah, we're in D6, so actually last to D5. So I would take the two cases, j equals 0 and j equals 1 separately, maybe. And maybe easier. So if j is 0, then r to the I, h is equal to, well, it's r to the I times r cubed. But of course, that's just r to the I. Well, we can use the fact that rotations commute. Rotations, well, not even rotations, it's just powers of r. Yeah. Powers of r commute. I guess it's really an example of using the associativity principle. Here you got a load of r's multiplied by a load of r's, but you're thinking of this as a product of I r's, then multiplied by 3 r's. Well, you just kind of move the brackets around. In total, you have I plus 3 r's there. You're just organizing that list slightly different way. Okay. So I'm saying powers of r commute. Powers of any group element always commute. Yeah. And then the r to the I can simply jump out to the right-hand side of the set. There, yeah. And that's h r I. Yeah. Good. So if j equals 0, the left coset is always equal to the right coset. If j equals 1, then a typical element here, and so I'm claiming that we don't need to consider separately the cases for I equals 0, I equals 1, I equals 2. We can just handle them all in one go. And similarly, I think for this case here. So what will this be? Well, this time this will be r to the I s, and then r to the I s after r cubed. Okay, so here we do have a little bit of work to do. A little bit. Yeah, so what are we trying to do? We're trying to put this r to the I s, we're trying to get this over the other side of R3. So I want to move these r's past s. But each time I move one of those r's past s, well, you see we're using this fundamental SR equals R inverse S. Okay, that's the relation given in the description that tells you how to move an element R past an element of S, how to commute to S of R. Okay, here we got 3 elements of R, so it's got to move to the other side as 3 copies of R inverse. Okay, so it'll be R to the minus 3 with S. Yeah. Yeah. So that's using SR equals R inverse S. Now we can write that. Now we can commute the R's as powers of any element commute as before. And then lastly, well, you see R to the minus 3 is actually equal to R3. Remember, R to the power 3 is rotation by pi radians. It is its own inverse. So that's just R cubed itself. And now you can factorize out the R to the power IS out to the right-hand side. So maybe a little bit of justification here as r to the minus 3 equals r cubed. Okay. R cubed is its own inverse. So does that look like a good, have we proved it's normal? Proved for every element, the left coset is equal to the right coset. We just did it in two cases. We dealt with the rotations, we dealt with the reflections. So every reflection can be expressed like this for some value of I. Okay? And there's no other elements in D6. Okay? So H is normal in D6. Okay, according to the definition. What will be the order of the factor group? D6 factored by H. There's an answer. What's the answer?
H3.
Uh-huh.
H3 is the order of the group divided by the order of the normal group.
Yeah.
Just the, oh no, because D, what is D6? It's got 12 elements, it would be 12 divided by 2, so it would be 6.
Yeah. So 6 is the order of the group. Okay. So we say here, this is really by Lagrange's theorem. Well, by the definition of factor groups. Remember, the factor group is built on the cosets. Yeah. And Lagrange's theorem tells us that the number of cosets is the size of the group, containing group divided by the size of the subgroup, index of the subgroup. So by Lagrange's theorem, we could say there are D6, the index of H of D6, which is equal to the simple quotient of their orders. That's 12 over 2, which is 6. There are this amount of cosets of H of D6. So the order of the factor group, the order of this single group, is equal to 6. We've justified that well. Refer back to Lagrange's theorem. Work in, showing that we know the index notation and so on. So that prepares you for part 3, which is to determine the elements of each of the left cosets of H and D6. So it wants you to specify really clearly what are the cosets. So knowing how many cosets there are prepares you well for that. It'll hopefully stop you leaving any out or duplicating them. Okay. So what's a systematic way to approach this? Well, I would just say, we'll just consider possible representatives, and we'll just discover the different cosets, and we'll be careful not to write down the same one twice or anything. So let us consider the elements D6 as representatives. And write down the distinct cosets we discovered. So what's the first element I should choose? There's one and only one answer.
Identity.
The identity. Yeah. So let's choose the identity element as the left coset. It's clearly going to be equal to H, and its elements are the identity and R cubed. Is there any other representative that would generate that coset?
R to 6.
R to the 6 isn't a different element. R to the 6
Well,
is the identity.
Yeah.
So is there any other element that would also generate
R to 3.
R to the 3? Yeah. So remember, every element in the coset is an equally good representative of that coset, so to speak. Yeah. So equally well, this would be r cubed times h. Okay. So I won't bother. I'm kind of noting down any other representatives. So I won't separately try and say, oh, let's see what coset r cubed generates, because I've already noted, well, it's going to generate this first one. Yeah. So that's number one. Number two,
R.
Yeah. Let's consider the rotations first. So what are the elements of RH?
R and R4.
R and R4. Yeah. So another representative would be R4. Yeah. Just whichever elements you see in there. And that makes sense, because if you construct R4H, you end up with the elements R4 and R7. Yeah. But remember, what's the fundamental property of R is R to the 6 is the identity. So R to the 7, you should interpret the exponent modulo 6. The 7 modulo 6 is 1. So again, we would just get R4 and 1 as well.
Yeah.
From R4H. So another one, wow, R squared. Okay. Ooh, why did I write H there? Sorry. Something like that. That's not right. R squared H is the R squared and R5. So clear, that's also represented by R5. See, at the end of this process, I'll have all 12 elements, on the page, so to speak. So which element should we take now?
The symmetry times
The
so just MS.
the reflection. S. Yeah. So SH is SR cubed. Now, I maybe won't leave it like that, because remember the standard form for the elements that were described in the question was R to the I, S to the J. So that's not quite in standard form, because the rotations are on the wrong side. Yeah.
Oh, yeah.
So I either want to have the rotations on the left and the reflection, if it's present, on the right. So which one is that equal to? What's the standard form of SR cubed?
R to minus 2.
R cubed.
Oh, okay.
Yeah. Or you first think R to the minus cubed.
Yeah.
R to the minus 3s, but R to the minus 3 is R cubed. Yeah. So that would be R cubed S. Okay. So this coset is generated by S, but it's equally well generated by R cubed S. Yeah. So 5 RS we haven't chosen. RS generates RS and RS R cubed. But to put that in standard form, RS and R4S. And that's going to be equal to R4SH. Well, so just one more. So it's going to be R squared H. We haven't mentioned that yet. It's going to be R squared S, R squared S R cubed. But that's just going to be R squared S R5S. So we pretty much answered that question. Determine the elements of each left coset. So I guess these are the preferred form, because here I've got all the elements in standard form. Yeah. Is you're all okay in what I was doing there? Kind of, Jordan? Anything unsure? So the point about doing the second representation here is to get these in get these in the standard form that's quoted in the question. And the standard form is good because once if you're comparing different elements in standard form, you can just inspect them. So I'm confident R cubed S is different from R4S.
Yeah.
They're both in standard form. It's when you're trying to compare this element with R cubed S. It's not immediately obvious whether they're different or not because this is a complicated product. Maybe it'll all work out to be the same as that, or not. Maybe it won't. So that's the advantage of bringing everything into the standard form.
Yeah.
You can then just inspect and determine whether they're the same or not. Of course, these ones are already in standard form here because they didn't mention S at all. So they're just a power of R. So that's already in standard form.
Yeah.
So you got your standard form representation there, those three, and the standard form representation there. And each coset, we've shown the elements. 6 cosets, that works out. And we've got 12 elements in total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's all the 12 elements of D6 partitioned into those 6 left cosets. Yeah. And that's all the question was asking. Determining the elements of each of the left cosets. Is there, the only justification for what I was doing there was the definition of a left coset and just using the relations R to the 6 is the identity and S squared is the identity, and what did we use? S squared is the identity, and the way to commute SR. SR is equal to R times S. So 4, assign suitable labels to the cosets and construct a Cayley table for the factor group. Cayley table. So I need a 6 by 6 Cayley table. So you need to sketch it out pretty bigly. Must be fairly large. Fit it on the table. Now, what would be sensible labels to use?
E.
E's.
R.
Yeah.
S. R2. R3, R4, and R5, wouldn't it?
Well,
maybe not particularly in that order.
The only thing is I'm using exactly the same labels that label elements of D6 to begin with. So I might confuse myself.
Yeah.
Use the reader. Yeah. I want to slightly avoid using, R could be used as a label for number 2, because R is a representative of it. But it might confuse slightly because R has a meaning already. I could just use these expressions here as labels. H, RH, R squared H. Maybe just use the name of the left coset. I think in the solutions I went fancy and brought in some Greek letters, I think. Yeah, I called these two row 1 and row 2. And I call these sigma 1, sigma 2, sigma 3. But I think, they're simpler names. They're only 1 character names, as opposed to some of these have 3 character names. I don't know. I'm tempted now just to use those labels themselves as the names. Or you use the names as the labels.
Yeah.
So the identity element is H. And you've got this element, RH, you've got R squared H. And then you've got SH, RSH, R squared S. And remember, if someone says, oh, where is R cubed S or where is R4S? Well, R cubed SH is this one. Yeah. R4SH is this one. But you just got to settle on one unique name. So those are my elements. So, do we need a note here? So just using the first representative we encountered. For each coset. We'll list the elements. List the elements of D6 as this list here. I won't write, I could write EH, but should I write EH or just H? think H is clear. Maybe to be consistent. Whatever. Yeah, let's be consistent. Like EH. EH. RH. So here I'm just setting up a regular K table. SH. RSH. And R squared SH. So maybe having lined paper might be slightly better there. So you've just got 36 entries to fill out. Yikes. But the first row is just a repetition of the row labels, yeah? So you're multiplying by the identity. So we're computing in the factor group now, remember? Maybe just put a reminder down here. Remember, how do you multiply two cosets? Which coset is this? I multiply a coset AH times BH. Which left coset is this? How do you multiply together two congruence classes modulo?
Just take a representative of each, multiply them in the class, and then do the coset.
Yeah,
and
exactly.
The original group.
Yeah. So which representative should I choose?
AB.
AB. Yeah. So it's the coset of the product. The coset represented by the product of the representatives. Yeah. So RH by RH is R squared H. Yeah. RH by R squared H is, they were tempted to say R cubed H. We're correct in saying R cubed H. But R cubed H isn't one of the names. No, so RH
that one times that one.
by R squared H. My first instinct is to write down R cubed H, but I don't because that's not one of the names in use. So it's EH again. Yeah. Remember, R cubed is the identity. So this is EH. This will be RSH. This will be R squared SH. And this will be, what's the last one there? SH, yeah. Tempted to think of it R cubed SH, but R cubed is R cubed SH, but R cubed SH is just the alternative name for SH. Yeah, I'm going to use SH because that's the name I'm using. I mean, it's maybe a little bit off-putting because you've got these multi-character names, the cosets, but they're very meaningful and they're, I think it's worth keeping.
It's been well defined by previous questions.
So
it's a matter of just taking exactly what you know.
Yeah, rather than
you couldn't get the answers.
Yeah, rather than substituting, oh well, let's call this one row 1, let's call this one row 2. Yeah, this maybe you're losing touch with what they actually are. So we go for the row R squared. This is going to be EH, and R squared H times R squared H is R to the 4H. But R to the 4H is just another name for R.
Oh, just R.
Yeah. R squared SH, R cubed SH. R cubed SH is just SH. So this has to be the other one, RSH. Yes, this one's going to be R to the 4SH, but that's another name for RSH. Making sense so far?
So far.
Yeah, so we just keep going. Okay, so now remember the row index is the one that goes on the left. Column index is the one that goes on the right. So multiplying these two, it's the coset SRH. But SR isn't in standard form. So in standard form, SR is
RS.
In standard form,
Oh,
SR is the product. Remember, this is the relation given in the question. SR is R inverse S.
Yeah.
But R inverse is R to the 5, yeah, because we're in D6.
Yeah.
So R inverse is R5. So this SRH is really R5SH.
Which is squared SH.
Exactly. That's the other representative for R squared SH. So this product here is R squared SH. That makes sense?
Mm-hmm.
And then this one has to be S R SH. SR squared. So that's equal to R to the minus 2S. R to the minus 2 is R4. And R4S is the other name for RSH. So I have RSH there. SH times SH is going to be S squared. H with S squared is the identity. So it's EH. Here it's going to be SRS. SRS is equal to R inverse. R inverse S squared. S squared. S squared is the identity. R inverse, which is R5SH. Oh, sorry, the S is gone, which is R5H, which is another name for R squared H. So that product is R squared H. You follow that? Yeah, each time?
I got it that time.
Yeah. Now a shortcut when you're doing Kelly tables is when you come to the last element, it has to be the one you haven't mentioned yet. Yeah. Every element, every row has every element once and only once. The same for columns. So the one I haven't mentioned yet here is RH. So that has to be RH. It'll check out when you actually do the product. So this one RS times R.
So is this RRS or RSR?
So this one, remember, this one goes on the left.
That's on the left.
So this is RSR.
RSR.
So what is RSR?
Right, well, so SR is R inverse X.
Yeah.
So at this point, it's S R inverse X. That is R to the 5. X.
Remember, it's RSR initially. So you move.
S, R, and then move that one over there. So it's R, R inverse.
Yeah.
And then R inverse S turned into R5. Was it?
Yeah, but look at what you've got. You've got R and R inverse beside each other.
Oh, yeah. Ah.
That's just
E.
E.
Yeah.
And so it's just the S.
S is left.
Yeah, because the R inverse S. Yeah. And this one is just going to have to be the reflection type one I haven't mentioned yet, which is R squared. H. So I'm just popping around now using the last one standing rule.
Oh, you are.
It takes a bit of time, I think, to fill that out, of course. But I don't think using the long names made it any longer, really, because otherwise you'd have to constantly be checking back and, looking up the definition of each year and new ones a bit easier. Okay. So that's it. So that is the factor group. Remember, this is the factor group D6H. Okay, any questions about that?
That's good so far.
So 5, Use your Cayley table to explain why the factor group D6H is isomorphic to another dihedral group. So the indication here is use your Cayley table rather than formally prove an isomorphism by setting up the map or something, but just maybe argue from the Cayley table. So apparently this is the Cayley table of a smaller, well, it's got to be smaller because there's only 6 elements of a smaller dihedral group. Of course, if there's 6 elements, you know straight away which dihedral group it is. So if this factor group is supposedly one of the dihedral groups, D1, D2, D3, D4, D5, 6, one of them. But we can tell automatically which one it must be by the number of elements, don't we? There's 6 elements here.
Yeah.
If you look at the general description of dihedral groups, in the dihedral group,
It's 2n.
Dn is 2n. So if the 2n is 6, n must be 3. So it must be that this is, in fact, D3. Yeah. So I think all we need to do is just make some observations from the Cayley table that just confirm that. Okay. So by considering numbers of elements, by considering numbers of elements, this must be isomorphic to D3. And remember, and like as soon as you list the elements of D3, I'm going to use rho now just not to confuse with R, because R has a particular meaning so far in this question. It's rotation by 2 pi over 6 radians. Yeah. But that's the dihedral group D3 in standard form, using rho and sigma to play the roles of R and S for D3. And just observe, you know, your R1 is behaving exactly like that. We've got the identity element. This coset, which has order 3, it's easy to see here, you know, when you cube this, R squared H is this. When you multiply that by RH again, you get the identity. That has order 3. So these 3 elements are the 3 rotation-like elements: the identity, the basic rotation, and the basic rotation squared for D3. Yeah. And these 3 elements are acting like the reflections. They each have order 2. Each of them squared gives you the identity element. And you see we get this pattern that a reflection after a rotation is another reflection type element. Whereas a reflection after another reflection, those 3 up here, so down in this quadrant, that always gives you a rotation type element. All those are the rotation type element. So, well, we need to say, we need to write something down. I just make some remarks about this. So from the Cayley table, we see that RH plays the role of rho, the basic rotation of order 3. And SH, RSH, and R squared SH play the role of reflections. Each of order 2. So I would maybe say so. Specifically, the isomorphism, or a isomorphism, would be EH is the identity, RH is rho, R squared H is rho squared, maps to rho squared, SH maps to sigma, RSH maps to rho sigma, and R squared SH maps to rho squared sigma.
Each of order 2, does it say?
For the reflections, yeah.
What is-
Reflections always have order 2.
Yeah, because every time you do it, just you go back to the identity.
You should do that once in your life. You should stand in front of a mirror,
With
right?
another mirror.
With another mirror, exactly. So when you stand in front of a mirror normally and you will raise your right hand, of course your reflection raises their left hand.
Left hand.
Yeah. But if you have a second mirror and
You
you
raise your right
look at your reflection through the two, when you raise your right hand, the reflection raises their right hand.
The
So-
reflection's reflection.
Yeah. So you're seeing yourself finally the way other people see you.
Apparently, when you do look at yourself in the normal mirror that reflects the right way that you meant to, that'd be quite disturbing.
It is off-putting, yeah.
Because you've never actually seen how you really look in real life in a normal mirror. So people
Exactly.
that have actually witnessed it have actually said that it's quite a not traumatic.
That's because when you
What, in a mirror that mirrors your
They've
exact?
got someone in art.
When you're looking at a double mirror.
A double mirror.
So you're finally seeing yourself as other people
Yeah.
see you.
An art gallery
Wow.
straight up, yeah. So
You
certain
do
things
look
I think
kind
they
of
get eyebrow, it's meant to be quite.
Disturbing. Oh wow, I'm actually very interested.
Because when you look at your reflection, you think, oh, I've got a little freckle there on that side of my nose, but it's actually on the other side of your nose. Really,
Yeah.
when other people look at you. But when you're at a computer and you're using Skype, most of the time they're showing you a mirror image.
Yeah.
So it's not actually what the people on the other screen see.
Mm.
They see the true image. And if
Right.
you look in the settings, there will be a setting of Skype or FaceTime, or whatever. If you look in the settings, there will be a toggle mirror mode or something like that. If you switch that off, so that the image on the screen you're looking at is actually the true image of you, it looks off-putting and weird. And you think, hang on, that door in my, the door in the background is on the wrong side. Well, no, it's actually been shown on the correct side.
Correct. Oh,
But
wow.
but it's not, because you're used to looking at mirror images of yourself.
Yeah.
So when you see a true image of yourself, it can be off-putting, and especially the one in real time.
The other one that I noticed today, oddly you mentioned about a double reflection, is that front of the buses on the 192, it has like the stickers, doesn't it? So when you sit on the top deck, it has stickers on the front, but obviously the backwards. But if
People
you
facing outwards.
If it's
yeah.
that, obviously when you look at it from the outside, it's obviously the correct way.
Yeah.
Then when you go inside and sit inside,
Yeah.
the top deck, it comes up, that sticker's obviously the wrong way around.
Yeah.
But then as I was looking out the window, I noticed that the reflection of the reflection, so
Yeah.
it mirrors the mirror image. And then obviously because it was backwards there, looking at the reflection again, it appears forwards again.
Yeah. Used to be this pub I used to go to as a student, and the wash hand basin of the gents was right in the corner of the room. So the two walls meet there, and there's a mirror on both walls.
Oh,
So when you stood at the hand basin, you were looking into two mirrors. So if you went this way, your reflection went that way. And, you went this, and if you had a few pints, you go, oh my God, what the hell's going on? It's all going wrong. Okay. Oh, flip. Too much waffle.
oh yeah. But
Right,
oh,
see.
fine.
We blast through really quickly. See, there's only 3 marks going for it. Must be easy.
Oh, cool then.
So we assume H and K normal. Both normal in G. They're both subgroups of G. And they intersect trivially. By considering carefully this product, which is a commutator, where all elements commute. So let's consider this HK, H inverse, K inverse. Well, you see, we can consider this as the conjugation by K by H first. And so that must be an element of K. So this must be a K1 times K inverse. So that must be an element of K, since HK, H inverse is an element of K as K is normal. So I guess here maybe if I hadn't said it before, I'd propose here the alternative definition of normality. So a subgroup is normal if when you conjugate any element of it by any other element, you remain within the subgroup. Yeah. But equally well, Equally well, I can take, so sorry, I should actually bracket them like that. Equally well, I can take HK, H inverse, K inverse, and bracket it this way. And then I'm looking at H times a conjugate of H inverse. Now H inverse is in H, and I conjugate it by something else from the group, so I remain in H. So this is just H by another H1. So I should have put there, that's true for some K1 in K. So this is true for some H1 in H, as H is normal. But again, that's just an element of H, because it's a product of two elements of H. Yeah. So therefore, the commutator HK, H inverse, K inverse is an element of the intersection, so it's equal to the identity. And then that implies, when you unroll that, multiply both sides by K, then multiply both sides by H, you'll get that HK is equal to KH as required. So that proves they commute, as the question asked. Okay, I better finish that because Ling is waiting to come in.
Nice job, actually.